Hello everyone. In this lecture, we will discuss about the relationship between P2, PC and PM in a three-phase induction motor. So in a three-phase induction motor, P2 is nothing but the rotor input power and PC is the rotor copper loss and PM is the gross mechanical power developed in the rotor. Okay. So if we take the induction motor, the power three-phase AC supply is given to the stator. Okay, so here the input power, let Pn be the input power given to the stator. So this input power has to supply the stator losses. Okay, here the stator losses include both the stator copper loss as well as the stator core loss. So input power minus the stator losses will give you the output power of the stator, which is given as input to the rotor. Okay, here we have the rotor. So rotor is given an input supply of P2. Again, this P2 rotor input has to supply the rotor losses. Here the rotor losses are nothing but the copper losses only, because the rotor core loss is negligible. Now this P2 minus the rotor copper loss will give you the gross mechanical power developed in the rotor. Okay. So that is P2 input to the rotor minus the rotor copper loss will give you the gross mechanical power developed. So if we rearrange these terms, then we can write PC is equal to P2 minus PM. Okay. So let this be equation number star. So now we are going to derive the relationships between these three, P2, PC and PM. Okay. So suppose T is a torque. Okay, T is a gross torque developed in the motor. Okay, so in general power can be written as omega times T, where omega is the angular velocity and T is the torque. So omega is given by 2 pi n by 60. So now we can write P2 in terms of torque as P2 is equal to omega s into T. So here omega s is equal to 2 pi ns by 60. Here P2 is nothing but the power input to the rotor from the stator side, right? So in the rotor we have input power P2 and output of the rotor PM. Okay, gross mechanical power developed. So we can write the torque in terms of both P2 as well as PM, right? So first if we write P2 is on the stator side. On the stator side, we have the synchronous speed, which is the speed of the rotating magnetic field. So we have to write it as omega s into T. So that is 2 pi ns divided by 60 into T. Let this be equation 1. Similarly, we can write PM. So PM is nothing but omega times T. Omega is 2 pi n by 60, where n is the speed of the rotor. Here PM is on the output side of the rotor. So the rotor will rotate at a speed which is slightly lesser than the synchronous speed. So here omega, so 2 pi n by 60 into T. So this is second equation. So now from this star equation, we know that PC is equal to P2 minus PM. So now we'll substitute P2 and PM in PC equation. So PC will become 2 pi ns by 60T minus 2 pi n by 60T. So taking 2 pi T by 60 outside, we'll get ns minus n. So this is PC. So this is equation number 3. So now we'll divide equation number 3 by 1, which will give you PC divided by P2. So that will be equal to 2 pi T by 60 into ns minus n whole divided by 2 pi T by 60 into ns. So 2 pi T by 60, 2 pi T by 60 will get cancelled. Remaining terms are ns minus n divided by ns, which is nothing but the slip. So PC is equal to S times P2. Okay. So the rotor copper loss will be equal to slip times the rotor input power. Okay. Similarly, we can derive the relationship between P2 and PM. So now from this equation, we can write PM is equal to P2 minus PC. We'll keep P2 as such and substitute for PC. So PC is nothing but S into P2. So now taking P2 outside, P2 into 1 minus S is nothing but PM. Okay. So PM can be written as 1 minus S times P2. So if we write these three, that is P2, PC and PM in the ratio form, we can write it as P2 is to PC is to PM as 1 is to S is to 1 minus S. Okay. So if we want to write P2 by PC, okay, then by seeing the ratio we can write it as 1 divided by S. Similarly, if we want PC by PM, so PC by PM, then it can be written as S divided by 1 minus S and so on. Okay. Now we'll solve one numerical. It is given that a 415 volts, 3-phase, 50 hertz, 4-pole star connected induction motor runs at 24 revolutions per second, that is RPS, on full load condition. The rotor resistance and reactance per phase are 0.35 ohm and 3.5 ohms respectively, and the effective rotor to stator turns ratio is 0.85:1. So now we have to calculate first thing slip, second one full load torque, third one the output power. Okay, if the mechanical losses amount to 770 watts. Okay, mechanical losses are given. So next we have to find out the maximum torque, next the speed at which the maximum torque occurs, and finally the starting torque. Okay, so now we'll first write on the given data. The supply voltage, unless otherwise specified, we have to take it as a line value. So the supply voltage line value is equal to 415 volts. So next the frequency F is equal to 50 hertz, and the number of poles P is equal to 4, and then the motor is star connected. Okay, it is star connected, and then the speed corresponding to full load condition, that is full load speed is equal to 24 RPS. We have to convert this into RPM. So we have to multiply it with 60. So 24 into 60 will give you 1440 RPM. Okay. So next rotor resistance and reactance per phase value are given. So resistance is equal to 0.35 ohm per phase. Similarly, reactance is also given, 3.5 ohm per phase. Okay. So next rotor to stator turns ratio is given. So this is E2 by E1 is equal to 0.85 divided by 1, or simply 0.85. Okay. So first we have to calculate the slip value. So since we have the speed corresponding to full load condition, we can find out the slip corresponding to full load condition. Okay. So this is given by ns minus n full load divided by ns. Okay. So ns is a synchronous speed, we have to find out. So ns is equal to 120 f by p. So 120 into 50 divided by 4, this will be equal to 1500 RPM. Okay. So now we'll substitute in SF equation. So this is 1500 minus 1440, speed corresponding to full load, divided by 1500 will be equal to 0.04. So this is a slip corresponding to full load condition. So next, second subdivision, we have to find out the full load torque. So full load torque value will be, formula will be K into SF into E2 square R2 divided by R2 square plus SFX2 whole square. Okay. So already we know the SF value we have found out. R2 and X2 values are given. So now we have to find out the E2. E2 per phase value we have to find out. And K is a constant given by 3 divided by 2 pi into ns. So ns is nothing but the synchronous speed in RPS. So now we have to find out E2 value. So from this turns ratio, we can write E2 is equal to 0.85 times E1. So E1 is the EMF induced in the stator, which is approximately equal to the supply voltage. So which is given as a line value 415 volts. So from this we can find out E2 line voltage, okay, which is equal to 0.85 into E1 450. So on multiplication we will get 352.75 volts. So now we have to find out the phase value for E2. So since it is star connected, So E2 phase value will be equal to E2 line value divided by root 3. Okay. So 352.75 divided by root 3 will give you 203.66 volts. So now we have found out the value for E2. Now we can substitute in the full load torque full load formula. Okay. So now the torque full load will be equal to K. K is 3 divided by 2 pi ns. So 2 pi into ns is nothing but 1500 divided by 60 multiplied by SF value. SF value we have found out 0.04 into R2 value 0.35 it is given into E2 square. E2 is nothing but 203.66. So E2 square divided by R2 square plus SFX2 whole square. So 0.35 square plus SF 0.04 into X2 3.5 whole square. So on simplification, the torque corresponding to full load will come around 78.0849 Newton meter. Okay. So we have to find out P out. The mechanical losses is equal to 770. It is given. Okay. So the formula for output power is the gross mechanical power developed minus the mechanical losses. So the gross mechanical power developed can be written as omega times T. Okay. So omega is 2 pi n by 60 and T corresponds to the full load torque. Already we have found out. Okay. So 2 pi n is 1440 divided by 60 into 78.0849. Okay. So this will be equal to 11,768.956 watts. So this is the gross mechanical power developed. Now the output power is equal to PM minus mechanical losses. So 11,768.956 minus 770. So this will be equal to 10,998.956 watts. Okay, this is the output power. So next we have to find out the maximum torque. Okay, so the formula for maximum torque is K into E2 square divided by 2 into X2. So this is a formula for maximum torque. So under this condition, the slip corresponding to maximum torque will be R2 by X2. Okay. So in the general torque formula, we have to substitute for SM as R2 by X2. On simplification, we will get K into E2 square by X2 square. So K already we know 3 divided by 2 pi ns, small ns. So 3 divided by 2 pi into 1500 divided by 60. So E2 already we have found out the phase value 203.66 whole square. So divided by 2 into X2 value given. So 3.5. Okay. So on simplification we will get 113.22 Newton meter. Okay. So next we have to find out the speed corresponding to maximum torque. This will be equal to ns into 1 minus slip corresponding to maximum torque condition. So slip corresponding to maximum torque condition is R2 by X2. So 0.35 divided by 3.5. This will be equal to 0.1. Okay. So now the speed corresponding to maximum torque will be 1500 into 1 minus 0.1. So this will be equal to 1350 RPM. So this is the speed corresponding to maximum torque. So finally we have to find out the starting torque. So under starting condition, slip S is equal to 1. So the starting torque will be given by K into E2 square R2 divided by R2 square plus X2 square. So K value we know 3 divided by 2 pi into 1500 by 60. So multiplied by E2 square 203.66 whole square into R2 is 0.35. This is the numerator. Divided by denominator 0.35 square plus 3.5 square. So this is X2 square. This is R2 square. Okay. So on simplification, we will get 22.42 Newton meter. So this is the required answer.